This is the first of 2 films about the electricity industry, about the generation and transmission of electricity. We shall explore modern power stations and find out how they work. But first of all, some laboratory experiments showing the basic principles. Electricity can be generated by taking advantage of electromagnetic induction. Move a magnet in and out of a coil of conducting material, and a current will flow in the coil. There's the magnet, and there's the coil. The coil is connected to a sensitive galvanometer. Watch what happens. A current flows in the coil only when the magnet's moving. When it's still, no current passes. Here's another magnet, a permanent magnet, like the one we've just used, but a different shape. We're going to make up a simple electrical generator using this magnet and this single turn of copper wire. It's fixed on an insulating handle and connected to the galvanometer. If we just move it around between the poles of the magnet, again a current passes through the copper wire just as long as it's moving. If we rotate it like this, we get an alternating current, which changes its direction, first flowing one way, then the other, as the coil's rotated. But of course the wires get all tangled up. This is what's happening. When the loop's moving through this position, the current flows down the right-hand side in this direction. But the loop continues to rotate, and when that side has come across to here and is moving upwards through the magnetic field, the current induced now flows in this opposite direction. So, as the loop rotates, current passes first in one direction, then the other, and alternating current is produced. The current along the yellow lead is first traveling one way, then the other, as the loop turns, while that along the black lead is always flowing in the opposite direction, first one way, then the other. Here it is again. Using just a single turn of wire, we get only a very small current, and as we saw before, the wires got all caught up in a very short time. So we can use this device. The same single loop of copper wire, but one end's connected to this copper ring on an insulating spindle, while the other's connected to the second copper ring. The insulated connecting wire passes underneath the first ring, then it's joined to the second one. These are called slip rings. We mount this device so that it can be turned by a crank. Each of the 2 rings brushes against a metal strip, so that there's electrical connection between the loop as it rotates and 2 terminals down at the bottom. Each end of the loop is always connected to the same terminal. We've now made an improved alternating current AC generator, although the EMF it produces is still very, very small. The galvanometer needle shows us that it is AC, alternating current, changing its direction regularly as the coil's rotated in the magnetic field. Remember, there's got to be constant movement to keep the current flowing. Instead of using this sensitive galvanometer, we can show that we are generating alternating current by using a cathode ray oscilloscope set so that it draws for us the current produced. a sort of wave changes direction. You can see how the current goes first positive, then negative, then positive again, and so on. Here's a different arrangement. Instead of the slip rings, the two ends of the same copper wire loop are now connected to one of two split rings, which are separated by an insulating strip. This is called a commutator. In this position, you can see how the right-hand side of the loop is connected to this terminal, while the left-hand side's connected to this one. When it rotates, the right-hand terminal is always connected to the side of the loop which is moving upwards, while the left-hand terminal is always connected to the side moving downwards. So current taken off from the two terminals will always be flowing in the same direction. And the galvanometer shows that this is so. We've now got a direct current, a DC generator. The cathode ray oscilloscope draws the pattern as before, and you can see that this time the trace never falls below the line. This is direct current. There it is. The trace never dips below the line, never becomes negative, that is, never flows in the other direction. This is a more useful generator, although it's quite a small one. The magnet's now an electromagnet, and the coil's much more complicated, but the principle's just the same. We're turning mechanical energy, turning the crank, into electrical energy. Watch what happens when we start using electricity to light the lamp. Handle's harder to turn. Switch off and it's easy again. When the lamp's on, we have to supply more mechanical energy because more electrical energy is required to produce light and heat energy in the lamp. To produce electrical energy, you have to provide mechanical energy. It's all a matter of turning one kind of energy into another. You never get anything for nothing. We're now going to look at electricity generation on a much bigger scale, but the same applies. We've got to provide other kinds of energy to convert into electrical energy. The source of energy at many power stations is coal, and we'll start at a very big coal-fired station in the northwest of England. This train's bringing 1,000 tons of coal, and it won't last long, as we'll see. It's unloaded, then taken by mechanical conveyors to the coal stacks. Burning this coal will provide energy, which in the power station will be converted into electrical energy. From the coal stacks, the coal is carried up to the boiler house. It's first fed to great mechanical grinding mills down at ground level, which turn it into a very fine powder. This is just one of the grinding mills which work 24 hours a day, pulverizing the coal. The powdered coal is next burned. Chemical energy is released as heat energy in the boiler furnaces. Here's a simplified diagram. The furnace is like a giant hollow box with pipes running up inside it. The heat from the burning coal boils water in the pipes, the boiler tubes, turning it into steam, which passes out through the pipes at the top. This steam, superheated to a very high temperature, passes along pipes to turbines. Here, mechanical energy is produced, as the steam makes the turbine blades rotate. This mechanical energy of rotation is turned into electrical energy by the generators. A big electromagnet, the rotor, rotates inside a system of coils, the stator, and produces alternating current, which can be sent out over the national grid system. The steam which has passed through the turbines is turned back into liquid water in big condensers underneath. The steam is cooled by cold water, passing through pipes. The condensate, the water, passes out at the left there, back to the boilers to be turned into steam again. We don't turn out anything like all the energy as electrical energy. A lot is unavoidably wasted as latent heat in the conversion back to water, but it's made as efficient as possible. Air is needed to burn the coal. It's drawn in from outside, and here's one of the huge ducts down which it comes. Each of the 4 boilers has 2 furnaces, supplied with air in this way. There's one of the big electric fans which draw in the air. The coal dust is blown along these orange-coloured pipes to be injected into the furnace. Every 10 minutes or so, a ton of coal is burnt at each burner. There are nearly 200 coal burners in the station as a whole. Here are just 2 of them. You can sense the great heat produced inside the furnace as the coal burns. Well below, at ground level, ash is falling from the burning coal above. You can see some of the boiler tubes, in which water is turned into high-temperature steam. Right at the bottom of the furnace, the biggest lumps of hot ash collect. The coal is burned up at a tremendous rate. In just 2 minutes, the 32 tons of coal in a railway wagon are used up. This giant shovel picks up 15 tons of coal, less than a minute's worth. Every hour for 24 hours a day, a trainload full, 1,000 tons of coal can be burned to make 2 million kilowatts of electricity at this one power station. An enormous amount of energy is consumed. The boilers and furnaces are enormous. Here we're looking down to the bottom. The boiler towers for 200 feet. And the superheated steam emerges in pipes from the top. All operations are controlled from here, the power station control room. Here are the instruments for just one of the 4 turbo generators. Steam is coming from the boiler at about 560 degrees C. It's led down these pipes to the turbine hall, where the electricity is actually generated. This is one of the 4 sets of generating equipment. This is where the steam enters the turbines, and the mechanical energy is produced to drive the generator. The steam's at over 400 degrees C as it enters the first high-pressure turbine. there's a chain of turbines to each generator. The noise is almost deafening as the turbines race round, driving the big generator. The generator housings are painted orange, and you can see them quite clearly. There are 3 other turbo generators in this great hall. Each generator at this station produces 1/4 of the total output. In the control room again, there's a great array of instruments and controls for each of the 4 generators. Each is sending out over 450 megawatts of electrical power. The station as a whole generates 2,000 megawatts, 2,000 million watts of electrical power. The power is carried from the generators to transformers and switchgear outside, then passes out to the national grid. A large number of power stations, getting their energy from coal or oil or running water or from nuclear reactors, feed electricity into the grid, which provides electrical power throughout the land. In the next film, we look at the way in which electricity is transmitted. And we'll look, amongst other things, at another way in which heat can be raised to produce steam to drive turbo generators. This station turned the chemical energy of coal into electrical energy. We shall visit a generating plant where the energy doesn't come from burning a fossil fuel like coal or oil, or from running water. Here at a power station in North Wales, heat produced by changes happening in the very heart of the atom, the atomic nucleus, is harnessed to produce electricity. We'll visit this nuclear power plant and find out some of the differences and similarities between a generating station using the old fuel and one using the new.